Okay.
So I'd like to introduce Ted Blank, who's been an old friend for a whole year.
At least.
Right? Or thereabouts. I heard you last at this time, first at this time last year at NEAF. Got really excited about it. Went to your conference. I talked to other people about it. I think this is a really exciting opportunity. So take it away, Ted.
Thank you very much. Appreciate it. Hi, everyone. Welcome. It's nice to see you all here. We have some handouts up front, so what I'd like to do, about halfway through the talk, what we'll do is we'll start those going around the room so that you all have them in hand. We'll save some time at the end. And if you have questions during the talk, feel free to ask them at any time. So what we'll talk about today is how to do some important actual science work with equipment that you already own. We figured that NEAF would be the place to find people who already had astronomy equipment and were wondering what else they could do with it. And it turned out to be true. You go out there on the floor, there's a lot of folks looking for additional gear, but they've also got lots of stuff at home that they want to make some use of. And this is an opportunity to help scientists learn a whole lot more about asteroids and it turns out about the stars that they occult as well. So it's an interesting field. Amateurs can make serious scientific contributions. Discovery of previously unknown double stars, shape and sizes of asteroids, improving the knowledge of their orbits, their masses, the positions of the stars and their proper motion adjustments since they were last characterized by Tycho or Hipparchus years ago. And we have opportunities to also discover new double stars by lunar occultations as well, when the moon passes in front of a star. You'll see some charts. And if you don't have that particular chart in here, we've got some graphs of those over at our booth, number 245. So come see us there as well. So we call this chasing shadows because that's what we really spend our time doing. It's hard to imagine that an asteroid 3 or 4 astronomical units out in space could cast a shadow on Earth from the light of a tiny star, but light travels in absolutely straight lines, and we take advantage of that fact by allowing, by predicting as best we can where that shadow will fall on the surface of the Earth and trying to be in the right place at the right time to capture the light of the star blinking out and coming back on as the asteroid passes in front of it. We'll talk about what you learned from that in today's talk. And some of the equipment, for the last 5 or 10 minutes, I'll just stop talking and demonstrate some of the equipment. So this simple setup up here would be all that an amateur would need to go out and do an occultation recording of a bright star. So what we do, IOTA, it's called the International Occultation Timing Association. We try to support, come on right in. We try to support everyone who's interested in doing this sort of work. We provide the predictions of where the asteroids will be, where the shadows will fall, the uncertainty levels around that, whether the uncertainty is large or small. We try to provide software. All of our software is free for predicting where the occultations will occur, where the shadows will fall, where the observers who are already interested in observing have decided to place their equipment so that you can choose a different cross-section of the asteroid to measure. And then we also provide the analysis and publication support for those of us who get data that goes into a scientific paper. The only actual equipment that IOTA manufactures or sells or is involved with is something called the video time inserter, which is this little white box here. And what this does is it timestamps every frame of the video so that when we video the disappearance of the star, that by going back and looking at the frames, we can tell exactly what time the star disappeared and reappeared. And those times are reported along with your location, making that your contribution to the, come right up front and sit down. That's your contribution to the measurement of the asteroid. It would be one chord and when it disappeared and when it reappeared. We have a giant manual. I think it's up to about 350 pages right now, freely available on the website, called the Observing Manual, a Complete Guide to Observing Lunar, Grazing, and Asteroid Occultations. Makes great reading. A few parts of it are a little outdated, but it's in pretty good shape, and it'll give you a nice background on how to do this work. Here's an example of a photograph of the lunar North Pole. This was taken, of course, by the Lunar Reconnaissance Orbiter, and you can see that there's some incredible detail here. We now know basically the entire moon's elevation with the laser ranging to accuracy of meters. But before that was the case, there was no way to measure the height of mountains and craters at the poles of the moon without doing some sort of occultation work. And so what people did was actually go out and find a star that was close enough to the moon that the north or south pole of the moon would actually pass in front of the star, and the star would be occulted by not the entire moon, but just by the mountain ranges at the north or south pole. And so you could actually see the star disappear and reappear over time as the moon passed in front of it. And if enough people did that, as you can see here, each of these lines represents an observer, and each of these dotted lines represents the time that this star disappeared for them. Putting those lines together and doing some interesting calculations gives you a profile of the mountains at the pole of the moon. It's a community effort. You need multiple people to do this, but they don't have to be very far apart, because every kilometer they are apart is another kilometer distance. And some of these mountains aren't that high, 2, 3, 4 kilometers in height. So over 1 kilometer, you might have 20 or 30 observers. They would do this, and then you get a highly detailed representation, a reconstruction of the mountainous nature of that particular cross-section of the moon. And this is, even though we know a lot about the moon's profile now, this is still a wonderful opportunity for amateurs to begin this hobby by going out and doing a graze. In fact, I'll try to show you a movie of one of those grazes right now.
You want to get the light? Okay.
Let's see. We should be okay. Hopefully we're alone. So you see here, this is a video recording of the moon. The moon is moving in this direction here, and we see it just disappeared. This star just disappeared. I think this is Eta Geminorum, grazing the north pole of the moon. We've got video timestamps on every frame of the video. It is now passed behind a large mountain. It's now back.
Wow.
The moon does move. There's nothing like seeing it with your own eyes, though. And so in this case, each pair of disappearance and reappearance times will be a separate measurement that you would report to IOTA. Now we're behind some sort of large mountain range, but the moon is still moving. Here comes our star again. I'm not sure if we'll get another disappearance or not. Oh, yep, one more little mountain, just blocking it a little bit. Oh, another one. That's a rich graze, lots of events. And you see the star is disappearing rather slowly. I believe that's because this star has an actual sensible diameter. And as the moon's mountains pass in front of it, they actually occult the star slowly rather than quickly. And it's a very large, close star. There we go. I think that's our final reappearance. So interesting, and the software that IOTA provides will allow you to choose the spot on Earth to stand where you'll see the greatest number of disappearances and reappearances. And a few hundred meters can make a big difference. Thanks. We can have the lights back on then. Thank you. Okay. All right, so here, yeah, so we just had our Eta Geminorum raise. And we also, as I mentioned, the discovery of new double stars or the confirmation of existing double stars is easy to do when the moon, when the leading edge of the moon, which is dark during the first quarter phase of the moon, passes over a star. And if you see that starlight disappear in one step, then you haven't seen a double star, but sometimes it'll disappear in 2 steps. And the relative height of the 2 disappearances tells you the relative brightnesses of the 2 components of the double star, this binary star system. As long as they're aligned in such a way that the moon is actually occulting one and then the other. If they're normal to the surface, you'll get 2, but if they're perpendicular to the surface, then they'll both disappear at the same time, and that depends on where you are on Earth. We had these 15 asteroids visited by spacecraft as of 2012. So for these 15 asteroids, we know an enormous amount. Their size, their shape, we know where every crater is, we've got mass data, we've got the orbital data. But that's a very small number. There are millions of asteroids in the asteroid belt, and hundreds of thousands of them have been characterized. And other than their orbits, we know very little about them. This gives you an opportunity to provide actual scientific data about the characteristics of those asteroids. This is a 2D asteroid distribution of the asteroids. So here we are in the solar system in the center, and we've only shown this out as far as Jupiter, but here's this enormous gap between Mars and Jupiter where the main asteroid belt lies. And we're actually doing some work with trans-Neptunian objects as well, TNOs, that are much farther out in the Kuiper belt, and those are much fainter. They move much more slowly. The fact that they move slowly means you can actually integrate multiple video frames and actually see the star that it occults. These TNOs typically occult only faint stars. They're so small themselves. It's very, very unusual to have them occult a star, but when they do, it's typically a faint one. But we can integrate because they move so slowly since they're so far from the sun. We got OSIRIS-REx going out to the asteroid Bennu starting in 2016, and it's going to land, we hope, grab on, we hope, scoop up some material or inhale it or whatever they're going to do. It's an interesting challenge, and bring that material back to Earth. But it's obviously very expensive. So we can do something similar to that here from Earth. We can also look at these asteroids, and this is the best image that the Keck telescope could give us of the binary asteroid Antiope that we looked at in 2011 with a large expedition of folks. That's the image we can get from Earth with the best equipment that we have. An asteroid occultation can give us much more detailed information about that asteroid, about asteroids in general. So here's the geometry, right? The star is out here someplace, way off to the side. The asteroid is moving past the star. It's casting its shadow on Earth. We've got 5 observers here, A through E. Observer A doesn't see the star occulted. Observer E also doesn't, but observers B, C, and D will see the star disappear for various lengths of time, depending on what part of the asteroid passed in front of the star for them at their location on Earth. So here's 90 Antiope from the adaptive optics at Keck. When the shadow of that binary asteroid pair passed across Earth, and it was headed through Oregon and then down across California, a little bit of Nevada. But you can see this is an enormous asteroid pair. They're 70 kilometers in diameter, each of them, and about 50 kilometers apart. So it covered a big swath. The shadow covered a big swath of California, and we put a whole bunch of people and a whole bunch of these small telescopes out across the state of California and Nevada and some in Oregon. This was done at one of the yearly IOTA conferences. We always choose our conference location and time to correspond to some occultation event, so in the middle of the conference we can all pack up, go out in the field, get some data, come back the next day, look at the data, and then continue with the conference. So it's really an active conference, and there's never any charge to attend an IOTA conference, and the next one is in Las Vegas, and one of the pieces of paper we have here will give you the invitation to come and join us in October. So this is the telescope setup that went out for this mobile occultation. I haven't counted these yet, but I think there's more than 50 individual scopes from about 25 people. And the shadow came this way across the state of California. And here's a little animation of what it looked like if you were out in space and you could see these little telescopes on the ground. Here are the locations of the telescopes. These are the imaginary shadows that are passing across the state of California. And each of these little blue dots represents the observer. And when that dot disappears, that's when that star disappeared for that observer. Now, of course, they couldn't see those outlines. We had no idea whether these two binary components would pass along the line of most likelihood or somewhere else. They ended up a little bit north, I think. But I think it's amazing. You see these this row of observers here. Watch how they reappear along the curve of the asteroid. This is the real data. The times of these are exactly correct, and I animated these to match the data as closely as I could. But obviously, the actual outlines of the asteroid from that data represents the scientific return from this investment of time, and here it is. Here's the results of that expedition. About 40 or 50 chords across these binary components, and we can see here that the outline of the times when people did not see the asteroid represents the shape of the body of the actual rocky body itself.
So
Yes.
Can I ask? I had looked at these images some time ago. Do you know Eberhard Bredner from Germany?
Yes.
He was there for the occultation,
Yes.
and he did not see an occultation. He was in the middle.
That's right. That's right.
That's
Yes.
right.
Eberhard Bredner from Germany came all the way from Germany.
Yeah.
Set his telescope up right here, I think on this green line,
Yeah.
and managed not to see an occultation by either component.
Lucky him.
Yeah, right. So, Mike, come right in.
That's more information.
But maybe it's very important.
Yeah, it is. Yes,
Information.
yeah, exactly. The miss is very important. But in this case, we have given Eberhard and the people who also observed the miss here in the middle, we've given them the title of Hercules observers, because it's as if they passed between the pillars of Hercules without touching them.
Yes.
Exactly.
Right. We also thought of calling them the Moses observers for parting the Red Sea. We weren't sure which way, but they get a special honor of being Hercules chord observers. A Hercules chord is one where the observer could not see either component of a binary asteroid. And last month there were 3 more people inducted into the Hercules chord Hall of Fame. There was another binary that somebody missed in the middle. So speaking of misses, the miss observations are very important. As you can see up here, on the top we've got 2 chords, the purple chord and the blue chord. And the purple chord is a positive, and the blue chord is not. And so we know that the edge of the asteroid must be somewhere between these 2 lines. Similarly down here, we've got, and this is an amazing operation, less than a kilometer apart, we've got the orange line, light orange line and the dark orange line. And we know that the edge of the asteroid is somewhere between those 2 because the light orange observer had a positive and the dark orange observer had a miss less than a kilometer away. So we've nailed down the edge of the asteroid to within a kilometer of resolution at 100 million kilometers distance. That's amazing for amateur equipment that you see in front of you. Hi, come right in. And we also were able to determine that the asteroid component had a huge crater on the side of it, something that the Keck adaptive optics, as good as they are, couldn't tell us because there just isn't enough resolution to do that. Now we not only know how big the crater is, we know how deep it is, all from people watching little starlight disappear in tiny telescopes. Imagine what you could do with a slightly larger scope, right? And most of you already own them. So we talked about observations already. And one of the other benefits is to take combine 2 different independent views of the asteroid and see how closely they match. There's a group in Czechoslovakia, I believe,
Yes.
that does what we call shape modeling. They monitor the light output of the asteroid as it tumbles in space. And then they try to go backwards mathematically to say what shape of the asteroid could possibly have given us that curve of light as the thing tumbles, and sometimes it presents a narrow end and sometimes a wide end, and sometimes it's darker on one side and lighter. So they build a 3D model of this asteroid, or multiple 3D models that match the data, and then asks us sometimes which of our models might best fit the actual asteroid outline as measured to high resolution by the amateurs in IOTA. And in this case, you can see that this one, 360 Karlova, this was the shape model developed independently from light curves, and here it actually matches quite well with the positive chords that we had. And I'll pass around this. This is data from an asteroid Polyzena, which on April 15th was measured and occulted. And you'll see here, and we have in the room with us Angelis from Greece, who participated in this and is responsible for some of the data, the lines across the asteroid. So some of these positive events are his.
Number 4.
And there he is, number 4, right? in Montreal.
Which asteroid is that?
And so we have the initial results that showed that the asteroid was ellipsoid in nature, which is pretty typical. But the modeling group had 2 models to choose from, and this data was able to help them determine that one of them should be thrown away and the other one matched almost perfectly with the outline that we measured. That 7 or 8 individual chords was enough to show them which of their models was right and which was wrong. So they can stop running overnight supercomputer simulations on this model and continue working on this one now and be certain that they've got the right version. So let me pass around the rest of these now that folks are in the room. We'll just make sure that everybody gets one, and then I'll save a big rush at the end. I'll let you start each of these separately. Go around. And then this guy as well. Driving crazy here. And here's another classic conversion model confirmation asteroid Hertha. You can see the cross sections almost exactly match the shape model. So wonderful correlation between two independent views of the asteroid itself. We also have here at our booth Steve Kennard from Gamber, Maryland, who was the first person to identify a satellite of an asteroid through occultation work. This was his occultation light curve from the asteroid, and he happened to continue to measure the light from the star and noticed that about 250 seconds later, the light from the star dipped and resurfaced again. Incredibly lucky to find a satellite, a moonlet of an asteroid on the same path as the asteroid, where the shadow of that tiny satellite happened to go right over his telescope. Very lucky. Very lucky. But we still, I think it might be Dactyl. But we still, now, so as a result of this, we now ask folks to record for 5 minutes on either side of the predicted time of the occultation and to examine their entire light curve, not just the part where the occultation occurred, but look for moonlets, look for satellites and asteroids, because there's no telling the next person could be me and it could be you to discover a satellite of an asteroid this way. And you probably heard that this asteroid Cariclo was clearly determined by a Brazilian team to have rings around it by seeing the occultation of the rings on the way in, the occultation of the star, and then the occultation of the star by the rings on the way out. And this is the first confirmation of rings around an asteroid by occultation science. So, what do you if you have a home observatory, you would attach a video camera similar to this one here. This is a small Super Circuits video camera available for about $130 from Super Circuits. It's very sensitive. It's a very low light camera, black and white camera, very sensitive to light, and has the output is a standard NTSC video signal coming out of an RCA cable. And you would send that into some sort of a video recorder and track the star, record the potential occultation. When the times come down, you'd say, okay, I've got an occultation. I can measure exactly how long it is by counting the frames. It's 30 frames a second on standard video. But how do I know the actual times of the start of the disappearance and reappearance of the star? The key there is this little video timer box that you'll see running on the television screen. You probably noticed during my video of the Eta Geminorum Grays, you saw those timestamps going across the bottom of the screen. What we do is we take this standard NTSC signal, run it through this little box, and which, if it were outside, would be getting a true GPS time. At the moment, it's giving us X's because it says, I don't know what time it is. I have no satellites in view because we're inside of a concrete building. As soon as you take that outside, the little 1 pulse per second light starts to blink, and the timestamps are laid across the video. So it passes the video through unchanged except for putting the time on every frame. When you post-process the data, you can look at that and read off the times of the frames on which the star disappeared and reappeared. Those are the times that you report, along with your latitude and longitude, which the box also measures for you. And there's a little switch on here so that at some time during your recording, you would flip this little switch, and it would put directly on the tape your latitude and longitude. So you have a permanent record right after the occultation of where this camera was. If you have multiple cameras and you throw them all in the box at the end of your occultation, then you take them out, you might not remember which camera went with which site. But if you remember to flip this little switch for 3 or 4 seconds before turning off the camera, it's right on the tape, and you can't mix things up. So that's why they did that. Very handy. So this little camera with this telescope I hesitate to call it a telescope at NEAF, but here we are. It's got a primary lens and it brings light to a focus, so I guess we have to call it a telescope. It's a piece of a Tasco binocular. For $35, you get 2 of these. You unscrew them and you throw away the other part. And this is a piece of gear that comes from Lowe's or Home Depot. It's a little plumbing. Plumbing under your sink tends to be, has an internal diameter of 1.25 inches. That probably sounds familiar to a lot of you.
Yeah.
Looks just like an eyepiece. So this goes right on the front of the camera. We've got a focal reducer on here simply to increase the field of view, make the star images a little tighter and a little brighter, but also to give you more of the sky so you'll catch that star and make sure you're pointing at the right place. Leave one of these out in the field. You can have multiple of these time inserters, but most of us have just one, and there's a technique by which you can put the time on the video, because these little video cameras made by Canon, we buy these on eBay for $30 or $40 a piece. These have an internal crystal clock, and they actually put the timestamp, the internal timestamp of the camera on every frame in a hidden track of digital data. And we have some software that will bring that out. So if you just timestamp with the GPS box before and after your occultation, we can interpolate in between and grab the actual time. So you don't need to leave this. This box is $234 here at NEAF with a discount. And you don't have to leave that out in the field. You can bring that with you and just stamp each one of your recordings. For dimmer stars, we use larger telescopes, an 80 millimeter, the Orion Short Tube 80, the little white one that people use for guide scopes. Very popular for stars down to about magnitude 9, and then down to mag 12.5. The Orion Short Tube 120, the 5-inch refractor, is about as large as you'd want to carry around and leave out in a field someplace. But we've got a setup for that using a Sears Craftsman sprinkler tripod. A lot cheaper than buying something over here from Stellar View or Disc Mount. And it works great. And a little Orion EQ1 equatorial mount with slow motion controls. Put that on there, aim it at the sky, start your timer and walk away. I have 4 of these set up, so I've left 4 of these out in the field and gotten as many as 3 positive recordings on them. Here's some of the cameras. The super circuits that I have here, another one made by Watech. They also make wonderful gear. And there are now some integrating cameras as well. So for faint stars where you're willing to sacrifice some timing resolution in order to see the star, you can integrate 2, 4, 6, or 8 frames and get, instead of 1/30th of a second resolution, you maybe get 1/4 second resolution, but you do get data because now you can see the star. Here's the version 2 of the VTI box, which had black cases. The version 3 has a white case. The difference is that the version 3 has the ability to output the serial sentences from the GPS. So you can actually use this box to replace a GPS antenna puck that goes into another device. It can be a general purpose GPS time signal presenter for software. So when I went to Las Vegas in 2013 for this Sophrosiny occultation, the occultation went across the country like this. Here's Nevada, there's Las Vegas down there. Las Vegas gets a lot of occultations. And so, I've been there 3 times and now we're going back a 4th time. And it's nice because the sky is pretty dry. If you can get away from the lights of the city, which we do, it's a pretty good place to do occultations. Here are the 4 ST-120s that I packed and shipped and checked as airplane luggage. They survived just fine. Because they're refractors, so collimation is not an issue. I don't know if 4 reflectors would survive airline luggage travel as well, but they did fine. Here's the cameras packed and a bunch of battery packs and wires and things. Here's what the car looked like when I got there and unpacked. Suitcases are up front. Here's all the gear ready to go. Hand warmers, it was cold. And we didn't want the batteries to freeze or the cameras to freeze, so in each little box went a bunch of chemical hand warmers to make sure that everything stayed nice and warm. This little yoga mat, that's not for my yoga practice. It turns out that's very useful. You pile all the gear for one station on the yoga mat, walk over, set it down, then you can kneel on the yoga mat and not put your knees in the mud. Fidelis is laughing because he's done this many times, I'm sure. Anyway, very useful. And a little TV screen here so that you can find the stars in the sky before switching your camera over to go into your video recorder. Best place, and there's one right by Lake Mead National Park. So I treated myself to that. Here's where I deployed the sites, 3 of them here near Lake Mead. There's the Hacienda Hotel. There's Hoover Dam. And one was way down here, down US 95. I leave this stuff in a box with a label on it that says, please don't touch. It's not a bomb, it's not a terrorist operation. Call me, here's my phone number. So far, I haven't gotten any phone calls, and nobody has blown up my equipment thinking that they might be saving the world. This is what it looked like, pointed up. I put some cardboard on it to make sure there was no dew forming on as much as possible. And I even put one of those heater packs here underneath with rubber bands to heat up the primary objective a little bit, as if you had it like having a heater coil. Yeah, heater.
I like your counterweight.
Band.
Yeah, I was gonna say.
Yeah, man. Well, the counterweight is.
Yeah.
I looked at these counterweights, and they weighed 12.5 or 13 pounds apiece, and I said, okay, if I check those, I'm into $75 for excess baggage weight. How about a bag of rocks? So, plenty of rocks. All I had to do was remember to go to Subway for lunch and ask for extra bags, which I did, and it worked. But how do you point these things? I mean, there's obviously no tracking going on in this situation. It's a little manual equatorial mount. Here's the star. It's in a field of the sky that's not particularly amenable to star hopping. The way we do it is by something called pre-pointing, and to me this has opened up whole new vistas in occultation science. This is the star out here. Can't even see it at this scale. That's going to be occulted. But if you were to point your telescope at this point in the sky and watch the stars drift through, all the stars on this red line would drift through your telescope eyepiece over the 2 hours and 45 minutes or so that you would have between here and here. So this is the same line of declination in the sky. The Earth is turning your telescope at the smoothest possible rate. The Earth never runs out of batteries. It never has a grease problem getting cold in the cold weather. Everything works great. So the question is, where on this line would you point your telescope in order for this star to be in the field of view at 2:45 a.m.? And the answer is at the time listed next to that little red line. So anywhere on this line will work as long as you do it at the right time. So for example, here at 23:25, we've got a bright star here and a quite reasonably bright star here that's very, very close to this line. And so if I point my telescope at if that star is at this position in my field of view at 23:25, then about 2.5 hours later, the star to be occulted will be dead center in that field of view. And if there's an occultation, I'll have about 2 minutes of drift from this left edge to the middle and about 2 more minutes of drift from the middle to the right edge, depending on the field of view of the scope, of course, to catch that occultation. And usually 3 or 4 minutes is plenty of time, given the uncertainty in these events is typically less than 30 seconds. So everything seems to work out pretty well. And even for a home-based fixed observatory site, where you're not totally certain that your polar alignment is accurate enough to go to some tiny faint star in some far off corner of the sky, you can still use this technique. Pick this star, track that star from 10 p.m. on, and at 11:25, turn off your mount. And that's it. You're now ready to record the occultation 2.5 hours later. And now you're absolutely certain that that star will be in the field of view at the right time. You may or may not get an occultation, depends on where you are, or whether the clouds come in, but you know you won't be pointed in the wrong place. So it's very reassuring, and it inspires, it helps inspire you to go out and do this kind of work when you might have had experiences like I did early on in my career at this, of spending an hour and a half trying to be sure that I was pointed at some faint star in some distant corner of the sky. I had piles of maps, I had my software, but you're sitting in a field in the dirt, and batteries are running down, and things are getting cold, and you just can't be certain. This takes all the worry out of that. So I now pre-point every time. Unless I go to observatory, like up in Syracuse next week, there's an occultation, and we go up there, and I will borrow somebody's fixed observatory site, and if they say we can track and we can go to with great accuracy, we'll just say you go to the star. We'll just track the star. In that case, the star would sit right in the middle of the video and never move, because the star would the camera would track it, and that works fine as well. Here's the little cameras that we use. If you do this mobile observing, programming one of these little Sony television remotes from the 70s allows that device to turn on this camera 5 minutes before the event and turn it off 5 minutes after. Otherwise, you're limited to 60 minutes of tape, and that way you could only do a 60-minute occultation. With this little gizmo, you can set these stations up all night. If you have a 4 a.m. occultation, you might have 8 hours to drive through the desert like a crazy person and drop equipment off in the dirt. But the idea is that this thing will take care of starting and stopping the recorder for you. So the result of Sophrosity was good. We had 10 positives and this excellent miss that constrained the edge of the asteroid. So the model came out very nicely. You see all the people who participated in that.
Very round.
Yeah, it's not as
How big is it?
this is 100 kilometers. So it's a huge asteroid. It's about 100 kilometers across, and it looks like about 150 this way. You see that my name does not appear here, though, in the list of positives. That's due to what they call the learning curve. School of hard knocks. I don't know what you want to call it. They say an expert is somebody who made all his mistakes on somebody else's contract. So I'm an expert now, because I think I've made all the mistakes, except I keep finding new ones to make. I can't remember what the mistake was. It's something to do with programming the remote for the wrong day. But all that work and, no data. But, you live and learn.
Ted, what's the dashed line?
Oh, I think the dashed line is the predicted center line of where the asteroid was going to go. So this one, the uncertainty was very small, or we got lucky. But it came right down Highway 95 here as predicted, and so everybody was exactly where they needed to be, and we got lots of positive results. And we didn't have to spread out way north and south of the path in order to be sure we got at least some data, because there was the position of the asteroid and star were known so well that folks just concentrated on staying in the middle. So for manual timing, though, there are lots of options. You can simply turn on a WWV shortwave radio and call out by visual observation the disappearance and the reappearance of the star by saying out and in. People did this for 30 years. With WWV playing in the background, and afterwards go back and analyze the audio recording and see the waveforms, and you can see where you yelled out and in, and the pips on WWV will be on the tape along with the recording, the announcements of the time, and that's you can get within a 2 or 3/10 of a second that way easily, which is great for especially for the bigger asteroids with the longer occultations. You can also use this app called Emerald Timestamp, where you can tap the screen and it will record the time each time you tap the screen. And it uses network time protocol to calculate the delay from the cell towers in. It doesn't use your cell phone time. It calculates what actual UTC is based on the ping delay that it gets as it goes back and forth several times to the time servers. So this is giving you true UTC time. You would never want to use your cell phone time. It could be off by 5 or 10 seconds, and you would never know. But this is not your cell phone time. That's the internally calculated time by the app. Or use a stopwatch, or just count seconds. Anything you can do to get data. And remember, if you don't see anything, report a miss, because misses are just as important as positives. So we have lots of software tools. One of the ones that I wanted to show you is called Occult Watcher. Let's see here. Here it is. So this program shows you a list of all the occultations that are predicted to happen in the next 60 days or so. It goes on for several screens. And you can tell it where you are and give it some filter criteria. You can say, I can't see stars less than magnitude 12. I'm only willing to drive 100 miles. And this is the kind of sensitivity, well, the magnitude of the star will take care of that. So then it says, okay, then I'm just going to throw away everything that doesn't match your filter criteria and show you the ones that you might be interested in from that point on. So here's this event called Eckhart. That turns out I'm going up to visit my dad in Syracuse next week, and this shadow happens to go right over Syracuse on Saturday night, a week from Saturday. So here's the event. So it's a big asteroid. The predicted center line is this line here. Oh, it's going this way, sorry. So it'll pass right over Rochester. One of our members, Brad Timerson, who did the data reduction for Magellas's data here, lives in Rochester, south of Rochester, so he's signed up for this. So the green line represents the center line of the asteroid. The blue lines represent the edges of the asteroid. So if it were to go exactly down the predicted path, its edges would trace these two blue lines. That's unlikely. So how likely is it that it will be somewhere near that? The red lines give us that 1 sigma uncertainty boundary. They say that we have a 66% chance of the asteroid's shadow falling somewhere between these two lines, and a 95% chance of it falling between these two lines, the 2 sigma lines. So it's a fairly well constrained solution, and right now and then the gray lines represent the chords on which observers anywhere in the world who are positioned in the shadow have announced that they intend to observe. So I know that Brad's chord is here, Bruce Berger's chord is here. I don't know who this, oh, that's Brad. I don't know who this is up in, this is probably
Guy, I think.
Guy Nason.
Yeah.
Yeah, in Mississauga, in Toronto. So at least 3 people have announced, and a 4th one who's somewhere else, either out here in the middle of the ocean or up in Western Canada. So if I was going to pick a site, I would try to pick a place somewhere between the chords that are already announced, if I was going to go mobile. If I have a home site, I just say, this is where I sit, my observatory, I'm opening the dome, I'm not moving the observatory, I'm just going to open the dome and take data. And that's okay, because remember, the guy who's on the same chord as you might have some sort of equipment failure, and you get the data and he doesn't.
So, maybe it's Dennis Gray, who's also in Toronto.
Oh, okay.
Dennis Gray.
Okay, but up this way a little more off the ridge. Could well be. Oh yeah, the names are down here. Dennis Gray.
Yeah.
Yeah. So chord number 1, right? So there we are. And then there's somebody here in on Cape Cod as well. Bernie Young. So there's an observatory at Cape Cod as well. So over time, as we get closer and closer to this, people who register, their chords will appear. So this is a .NET enabled application that again is free to download, install on your computer. You can sign up with your email address, and then it will know who you are, and you'll know who we are.
Excuse me.
Yes.
Any issues with doing this site from the rooftop of a building?
No issues at all.
Nothing at all.
That'll be fine. If that'll get you above street lights.
Yeah.
Awesome.
Yeah.
Yeah, no problem. The only thing I can, for photography, you always say, well, or for visual observing, the heat from the roof,
Right.
all that sort of thing. But again, here all we care about is the time of disappearance and reappearance, and that's not going to be affected by.
And polar alignment doesn't play into it or anything like that, or?
Other than the tips of your tripod legs sinking into the asphalt
Right.
on the roof, that sort of thing could be a
Yeah.
problem. But if you're going to,
I have a solid roof, so.
Okay, yeah, no problem at all. If that's where you want to observe, more power to you. But again, I'm not sure, unless there's a streetlight problem, why not be on the sidewalk? It's just that much easier.
But yeah, there's too many streetlights.
But that's what you have. So that's what I figured it had to be. Makes sense. Okay, so let's go back to the presentation then. So here's our booth. This is last year's booth, but we're out there again this year in booth 245. You want to come on by? We've got a couple of posters here with some other detailed information about stuff. This is a light curve of a grays. We've got some more stuff on the entipy occultation. This is an example of a light curve of a double star. So if you come by, we can show you that. It's very interesting stuff. And I'll stop here and ask you if you have questions.
You ever get any information from, say, if Mars occulted a star? Something that far away?
I know that there have been occultations of stars by Saturn, and they monitored the light of the star passing through Saturn's rings in order to do occultation measurements of the density of the rings. But I think the camera in that case was on a spacecraft orbiting Mars. I mean, orbiting Saturn, but probably Cassini. I don't know for sure if we've gotten data from planetary occultations that took much use, although Pluto, I think the atmosphere of Pluto was discovered by an occultation. Right here is our discovery.
I have a picture of it.
Yeah.
And the distance is irrelevant. I mean, the only thing is that the shadow is cast. And it could be Kuiper Belt 80 AU away, it wouldn't matter. The only problem with something that far away is that it's harder to predict, because a milliarc second at 80 AU is a big amount on the Earth, whereas for the asteroid, a millisecond is
A lot less. Yeah,
So-
3
so-
AU instead of
So in
80.
other words, if you made an error of a milliarc second, a thousandth of an arc second, in where a Kuiper Belt object is at 80 AU, you're talking hundreds of kilometers on the Earth. So that uncertainty you showed in the ground track then becomes huge compared to the object.
Right, right.
And that's
It may-
why it's so hard to predict.
It may include the entire planet and space on either side. That's a huge uncertainty.
Yeah. That's why it's hard to do Kuiper Belt objects.
Exactly. But it's even, percentage-wise, it's an even better value proposition because it's so much more expensive to go there. If you do get data, you've saved a lot more of NASA's money than you would for an asteroid. As hard as it is to get to asteroids, it's even harder to get out to the Kuiper Belt area.
So did any of your people do Kuiper Belt objects?
Absolutely.
Okay.
Absolutely. It helps. As I said before, integrating cameras are useful out there. The stars that they occult tend to be faint, but because they move much more slowly relative to the star background than asteroids do, you can integrate and lose some time precision and not lose a lot of precision on the location of the asteroid and the chord across the asteroid, because they tend to be longer events.
And they all turn out to be circular.
That I couldn't tell you. It could well be, but I do not know. I don't know if we've had any multiple chord events on the same Kuiper Belt object at the same time. So, you need at least 2 chords to be able to tell if the thing is some sort of shape model. But at least even 1 chord tells you where it is, and that's important because that really improves the location accuracy of the object and of the star behind it. So there's lots of data to be gained there.
How about man-made satellites?
Yeah, I haven't seen, there are people who track man-made satellites
Yeah.
for a hobby. They love doing it, but I don't
You could get
believe
information on the star, at least.
you could, but they move so fast compared to the asteroids that the occultation of a star by a man-made satellite would probably occur within a single video frame. And
Wow.
therefore, you couldn't get any useful disappearance and reappearance times out of that.
Even the geosynchronous ones?
The geosynchronous ones, except they don't move with respect to the stars at all because they're geosynchronous. So they never occult anything. But the ones that are closer do.
You showed the lunar rays, but it's worth mentioning that if you have very, very high-speed equipment, when the moon occults a star, you can actually measure the diameter of the star because you can measure the diffraction pattern or lack thereof when the star disappears.
Star's big enough.
So what you're looking at is the couple of thousandths of a second that the star disappears.
Right.
And from that,
Wow.
you can measure the diameter of the star if it has a sensible diameter.
Exactly.
And we were doing that at Lowell Observatory back in the 70s
With high-speed equipment.
with very high speed.
And of course, you need to start with lots of aperture so that each of those thousandth of a second exposures has enough photons in it to give you a sensible image. But at Lowell, I'm sure.
But it's another occultation technique that nobody ever remembers to mention, and yet it was very useful.
High-speed
It's the only way to
optometry.
measure stellar diameter.
That's right. Well, we do lunar occultations today, even with 30 frames a second. If the binary components are far enough apart, we can get 5 or 6 frames of the intermediate light curve level before the second component disappears completely. And that's usually enough to characterize the relative brightnesses of the 2 components. And if you have 2 observers, seeing it disappear at different positions on the lunar on the lunar limb you can actually compute the position angle of the two components from the same observation, from two observations of the same event, because the moon has different tangential angle at different spots on the moon. But you know, so all this science can be done with equipment you already own. Yes.
This stuff help out in the orbits of the particular asteroids?
Absolutely. Many times we'll get an estimate of asteroid occultation time,
Right.
and there will be a little time uncertainty. It'll say plus or minus 3 seconds is the estimate of the uncertainty, and then the darn thing arrives 30 seconds early. So right away, the scientist who made that prediction knows he's got to go back to his numbers and look for the error, because he says this time plus or minus 3, and we've got it coming in 30 seconds early or 30 seconds late. And having a positive observation in that case goes right back into the asteroid orbit calculations and improves them for the next time. So there's a lot more asteroids than there are observers, so we do need all of you to participate. So I thank you for your time, and I'll hang around for more. Yeah.
I was going to say that the nice thing about asteroid occultation is that you don't really have to travel very far, or travel at all, because on average there's so many of them that sooner or later one or two is going to pass directly
Absolutely.
over you.
The two maps that I handed out here, the green one and this is the map of all the occultation shadows that are going to occur over the United States in the next 7 months, from now into December. So you see, you can't even see the outline of the U.S. on this. The green chart that you have is the tracks of what we call the easy occultation events. So those are brighter stars being occulted by larger asteroids. So a 50-kilometer asteroid occulting a magnitude 10 or 9 or 8 star is a very easy way to be pretty sure you're going to get a positive occultation result.
Looks like one goes right over Hampton.
Exactly. I don't know what the date on that is, but a Occult Watcher will tell us. So if anybody, if I can bring up the software, I'll show you how we analyze the light curves. You're welcome to stay for that. We've got another few minutes. I think the data is on here. I think the program, is on here. So this is the program that we use to analyze the light curves. I'll see if I can open up an AVI file here. Let's go to the desktop. Oh, it's in the light. That's right.
While you do that, can I give a commercial?
Sorry?
Can I give a commercial?
Yeah.
Okay, I'm giving the next talk. It's going to be on the Larry program, which is the Lowell Observatory Amateur Professional Collaboration.
Excellent.
But I wasn't sure if it would run long enough, so I thought I'd say something about occultations too. So since Ted was talking about asteroid occultations, I'm trying to, I have a couple of slides talking about other things. So if you sit through the Larry talk, you can get more occultations. Thank you.
Right. So here's a video of a star drifting across a field of view. So one of these two stars, I believe, is the star that's going to be occulted. This is a hot pixel in the camera. There are several of those. Everybody has those problems. So you can see this star is right at the limit of my ability to detect it with the camera and telescope that I had. But so you can see how slowly these stars drift across the field of view if you have a telescope with a wide enough field. We'll just let this. I think it's just pausing for a moment.
If we could place the circles on the star
Oh, we got to the end.
for the
Sorry.
measurements.
That is the end.
I mean,
I think there's an occultation in here.
may I? May I?
Yes, yes. Yeah, it is the bottom star. Yeah, I see it disappearing. Okay, so I'll do this again. We'll track that star. Put this up to here. Right there. Yes. There. We'll do drifting here. We'll hope it tracks successfully. Start the data. So we're now trying to track this star through its occultation. So this program is doing a photometric measurement of the amount of light in that little circle, the red circle, each frame of the video, and it's also tracking the star across as it drifts across the field, and it's doing a fairly good job of tracking it. Okay, yeah, there we go. So it's still there. I think that we have passed the occultation time now. So if we graph that, all right. So it's hard to see that when you look at the video, but now you can see the data shows the star before, after, and during the occultation. By I can't remember which star this was, which asteroid this was, but we had it was you could sort of see that in the video, but digitizing it and doing an actual quantitative measurement of the amount of light in each pixel gives you the actual answer of when did the occultation start and when did it end. And if I'm not mistaken, I think the software was processing the. Okay, yeah. In many cases, I see. In this case, you'll notice there are no timestamps along the bottom of the screen. That's because this was a mobile deployment, and rather than leave behind the IOTA VTI box, I just put a timestamp on the video before and after this event, and then went back afterwards and interpolated between those two times and was able to extract the data from it, and using another program called Virtual Dub, VDub. So there's all this free software out there, but we have lots of videos on the web showing how to use it. Okay, so now we're really out of time. We got to get out of here in time for Larry to talk. So thanks, everybody.
Thank you.